Welcome to Level 2 Physics. We're working on this electricity exam and we're attempting the 2023 question. So, what are we being asked here? A set of parallel plates 0.05 meters apart are connected to a 12 volt supply. Show that the value of the electric field strength between the plates is 240 and state its unit. So what it's asking us is, what is the strength of this electric field? So look at your equation sheet. Look at all the equations we've learned about so far. What equation is going to help us figure out how to work out electric field strength? Pause, come back to the video, and let's see what you've got. So part A, this is worth and achieved. The equation that we're going to be using is E equals voltage over distance. This will help us work out and confirm what the electric field strength is. So let's substitute what we have. They've given us a voltage of 12 and the distance between the plate is 0.05 meters. Plug that into your calculator. What do you get? You should get 240 volts per meter, and that's the unit. So that's part A done. If you've done all those things, you would have gotten that achieved. Next question. On the diagram, draw the electric field lines to represent the field between the plates. Okay, so what we have here is obviously this diagram, okay, and we see that it's connected to a battery. One end of the battery has a long stick, and then the other end of the battery has a short stick. So based on notes I've given you and previous video tutorials, this long stick indicates the positive terminal and the short end indicates the negative terminal. So this must mean that this plate is positively charged and this plate is negatively charged. So when we establish what plate's what, then we can start drawing the field lines. And you should know that field lines always point away from the positive charges and towards the negative charges. And in this situation of charged plates, remember that there are some field lines that are going to curve on either end. Okay? So take a minute, pause, give this a go yourself based on the clues I've given you. Should be a lot easier now. And then once you're ready, have a look at the answers. So this is what we have here. We've got the positive plate, the negative plate, and then we've got some field lines. I know you'll do a much better job than me, okay, because what is actually expected is that you have evenly spaced lines. They're all pointing downwards. There are curved lines at the end, and the lines meet the plate at 90-degree angles, okay? So carrying out this checklist and applying it will give you a merit for this part of the question. Part C. Use physics principles to explain how the electrostatic force on an electron would vary as it moves from the negative plate to the positive plate. Okay, so we're looking at electrostatic force. Remember, electrostatic force is the force between two oppositely charged things. Okay, so it's between a positive and a negative, and that force is the direction of the pull that they have towards each other. So if we have an electron in between the plate, okay, it is going to be attracted to the oppositely charged plate, all right? And so what the question is asking us, how does this force, this pull, change as it moves around the field, okay, as it moves from the negative plate to the positive plate? Have a think, and when you're ready, you can come play this video again. So I want you to keep in mind, okay, now that you're back, I want you to keep in mind that the field that we're dealing with is uniform. It's constant everywhere. Okay, it's all even, the electric field strength is all evenly spaced around here. And so because the electric field is uniformly distributed, or it's just a uniform field, the force at any point is going to be the same, okay? The level of force is going to be the same. Don't get energy mixed up with force. The energy might be different, okay, at a different point of the field, but the force is the same. So what we have here is, since the electric field is uniformly charged, the force on the charge will be the same anywhere. And that is because of the uniformly charged field. All right. Part D, an electron is moved from point A to point B as shown. Calculate the change in electric potential energy as the electron moves from point A to point B on the diagram. Okay, so look at your equation sheet. What equation are you going to use to work out the electrical potential energy? Pause, come back, and see what you got. So this is the equation that you should have identified. And now we're going to use this equation to basically answer the question. So we're calculating the change in electrical potential energy. Do we have all the values that we need? Well, if we look at the information provided, we've got electric field strength, okay? Do we have a charge that we're dealing with, and do we have the distance between the plates? Go find that information in the question and then come back to this point of the video. So once you have all that information, you should substitute everything in. So we've got the electric field strength, we've got the charge of an electron, which is on your formula sheet, and then we've got the distance between the plates, which is provided in the question. Plugging all of that into your calculator, this is what you should get, okay? The minus sign, okay, shows that's an electron, and it gives your final answer as a negative. Don't freak out, okay? Usually if you look at the exam answers, they kind of discount that negative. They don't include that within their answers. But what you should say when you get a negative answer, or if you use the negative value, is you should use the value and explain why it's a negative. So what I've written is 1.92 times 10 to the power of negative 18 joules of electric potential energy is being transformed into kinetic energy as it moves from point A to B. So that kind of confirms my understanding on why it's a negative, okay? Because it's the potential energy being transformed or reducing while it increases the kinetic energy, okay? So it's being lost and transformed to EK, kinetic energy. Okie doke. So, second part of the question that we're dealing with, the electron is now moved 0.05 meters from point C to point D, as we can see here. What is the change in electrical potential energy as the electron moved from point C to point D? Okay, so we know that if it were to move from point A to point B, the electric potential energy is decreasing as it turns into EK. Okay, it's got a high amount of EP up top, a high amount of stored energy here, and then as it moves down, that energy is being converted into EK, so it lessens. However, if it's moving horizontally like this across the field, okay, think back to your notes. What do you think is going to happen to the potential energy? That is right. It is going to stay the same, essentially. It's not going to change because it's the same distance away from the plate from point C and point D. It's the same distance. And so that's why EP is not going to change, okay? Because it's moving across the field lines and it's the same distance away from the plate than it began. So the answer for that is there is no change in electrical potential energy because the charge is moving horizontally across the field lines. All right, that is worth an excellence, and we've finished our question for 2023. Hope that made sense. Please email me if there are any questions or anything else that you would like to clarify. Otherwise, I'll see you in the next video.